This is the third and final part of the 20th lesson in heat transfer. In the final part of the lesson, we will discuss and define the mass average temperature of an internal flow. The mass average temperature is also sometimes referred to as the mean temperature of the fluid flow. By the end of this lesson, you should be able to explain how the mass average temperature is defined. You should also be able to derive an expression for the mass average temperature given the velocity and temperature profiles in a confined flow. Finally, you should be able to explain why the mass average temperature is useful in engineering analysis. On with the lesson.
My main goal for you in understanding the mass average temperature is to understand what it represents physically. So all this mathematics is really just to help you understand what it represents physically. So in the end, I'll give you a chance to try to capture for yourself, however it's easiest for you, what this mass average temperature means. Like, what is it? Okay, because this is going to be the reference temperature now for Newton's law of cooling. Whenever we have H times delta T in Newton's law of cooling, that delta T is going to be T minus the mass average temperature of the fluid in the tube, right? Because that's the best reference temperature to use for the heat transfer in internal flows. Okay, so I tried to sketch a tube like this. Very difficult on these digital pads. And what's happening here is that we have heat transfer flowing, or we have fluid flowing in and fluid flowing out. And then I also drew a section view. So we're just looking down the tube, looking over section AA. And I drew this ring, and we'll get to this ring a little later. But first, I wanted to just kind of like jog your memory from thermo. If you would have had this problem in thermo, and someone would have said, please, analyze that with the first law of thermodynamics, you would have said, this is an open system. So I need to use the open system governing equation, which looks like this, probably, is what you remember it. And we recognize in this particular problem that there is no work, all right? So that goes away. And then you have these kinetic energy and potential energy terms. Those were the, V squared over 2 and the GZ, yeah? But there is no potential energy change, right? It's a horizontal tube in this case. And there is no significant change in the velocity, right? So there's no change in the kinetic energy of the fluid. It still has the same velocity, right? It does have a lower pressure, right? Because it's the pressure potential that's used for overcoming the friction, not the kinetic energy. So those go away. So in the end, you would say, well, okay, if there's some heat transfer in, that heat transfer must give rise to an increase in the enthalpy flow rate, right? We'd have m dot times h out minus h in. But that m dot times h out minus h in, right, just represents like it's the rate at which enthalpy is flowing out of this system relative to the rate at which enthalpy flows in with this system. And if the heat transfer is in, right, that heat transfer causes the enthalpy of the fluid to increase, right? Because enthalpy is how we attach energy to mass that flows across the boundaries, right? So that's the important thing here to remember. And then, of course, we took advantage of the fact that there is this relationship between enthalpy and temperature, right? It's related through the specific heat at constant pressure, although for an incompressible liquid, constant pressure, constant volume doesn't really matter, right? C sub P is the same as C sub P, basically. And if we treat that specific heat to be constant, then this differential becomes a total change, right? And we can just represent changes in the enthalpy by C sub P times a change in temperature. So when you sub that in, then you get this m dot C sub P times T out minus T in. And what's important to remember is that this actually represents this, right? So like we have a temperature here, but it physically represents this. This is the more fundamental thing. It represents the enthalpy flow out relative to the enthalpy flow in. So the real question is with this temperature, like what temperature are we talking about? Because we anticipate, right, if we're heating the fluid up from the outside in, the temperature at the outside probably is not the same as the temperature at the inside. And so what are you talking about? Like what's the T really represent? What T are we talking about in the fluid, right? What temperature is this thing? And of course, it is the mass average temperature. So the way we can get there is to recognize that when we look at the section over here now, section AA, if you imagine the fluid is flowing at you and it's being heated from the walls. So it's being heated from out here, right? It's going to be hotter near the wall where the heat's being applied than it is at the center where the heat's, that's far away from the wall. And so if you think about a little tiny ring of fluid flowing at you, that ring has a different temperature depending on where you are in the radius, right? Of course, there's also no slip condition. And so there is no velocity of the fluid near the wall, but it increases as we move away from the wall. So this ring also has a different velocity depending on where we draw it, right? So if we want to represent the enthalpy flow rate, we really need to think about the enthalpy flow rate through all of the little tiny rings that we can draw and then add them all up. So let's do that. So here's the enthalpy flow rate through one ring, right? So I'm just saying the ring is differential. So I have an H dot with a little d in front of it, but the H dot represents the same thing. It's the enthalpy flow rate, but this is the little tiny differential piece associated with this one ring. And I can represent that just like we did over here, m dot times H. Same idea here, right? It's like whatever the mass flow rate is through this ring times the enthalpy of the fluid in this ring. If I multiply that together, this is the specific enthalpy in joule per kilogram Kelvin, right? So when I multiply by a mass flow rate in kilogram per second, I get a power in watts, a joule per second. It's the same idea. So I would calculate the m dot just like I would, from thermo. It's the density times the velocity times the area, right? What's different here is that it's the velocity in that particular ring, and which, where the radius is, the velocity is going to change. And the area is differential, right? So it's this little tiny ring strip. And that differential area is 2 pi r dr. You can get there a couple of different ways. I imagine cutting the little ring and unfurling it, yeah, and making it look like a rectangle. And then one side of the rectangle is the circumference of the circle, which is the 2 pi r. And the other side of the rectangle is dr, which is how tall it is when you cut it open and stretch it out to be flat. The other way you can get here is you could say the overall cross-sectional area of this section is pi r squared, right? It's the area of a circle. So take the derivative of pi r squared with respect to r, right? You have 2 pi r, and then you have the derivative of r because that's what you're taking the derivative r. So it's 2 pi r dr. So that's the area. And then if I want to represent the enthalpy of the fluid in the ring, I can just use that delta H equal Cp delta T, right? So I say it's Cp times some temperature, where the delta H, this delta T, right? If we just assign like a reference temperature, we just set it equal to 0. That's basically what we're saying, right? And then I multiply all that stuff together, right? And I end up with this expression for the enthalpy flow rate through a single ring. It's 2 pi times density times the specific heat times the radial location of the ring times the velocity of the fluid in the ring times the temperature of the ring times the thickness of the ring. That gets me the enthalpy flow rate through the ring. Now, that's all fine and dandy, right? And if I want to get all the total H, I have to add up the contributions from all the rings. So that's where the integral comes in. We just, to go from dH to H, we integrate with respect to R, from the center line to the tube wall. And if we have an incompressible fluid, there's lots of constants in here. 2 pi is a constant, density is a constant, specific heat is a constant. All that gets pulled out of the integral and sits in front. Okay. But we don't want to have to do this all the time, right? What we really want to be able to do is take m dot times C sub b times some temperature value to get to the same enthalpy flow rate, right? To get to the same H dot here. So we can do that. And all I've done on this line is I've substituted in for the overall mass flow rate, the density times the average velocity times pi r squared, which is the cross-sectional area. So if you set those two things equal to each other, this right-hand side equal to the left-hand side, we'll be able to figure out what the mass average temperature, how it's defined, right? So this is all I've done. I've set the left-hand, the m dot C sub p Tm equal to the integration of all of the enthalpy flows through the rings. And we get some cancellations, right? Because there's a density on both sides, there's a pi on both sides, there's a specific heat on both sides, all that comes out. And if I then take that equation and solve it for T sub m, that's it, right? That's our definition of the mass average temperature. So that's how we could calculate the mass average temperature if we knew what the velocity profile was and the temperature profile is. And we know what the velocity profile is for fully developed laminar flow, right? I reviewed that on Monday. It's a parabola, right? It's a parabolic function. we don't yet know how the temperature changes as a function of the radius. So we're not in a position yet to calculate the mass average temperature from the variation of the properties over the section, right? But that's where this comes from, right? So when I see mass average temperature, it also goes by the name mean temperature, if you like that better, or mixing cup temperature. I think this is the temperature that when I multiply by the mass flow rate and the specific heat of the fluid, I get the right enthalpy flow rate, right? That's what it really represents. It represents the enthalpy flow rate because it ties all the way back to this thermodynamic idea, right? That we want to be able to represent the enthalpy flow rate of the fluid flowing down the tube because that's the thing that's linked to the heat transfer. So that's all that this is. So take a second, all right? However you want to capture this idea for yourself, do so in your notes. I'll give you a minute. All right? So what is the mass average temperature? What does it mean to you? Can you explain it in your own words?